So today we'll talk about global register allocation. So in the previous lectures, we talked about local register allocation within the same basic block. Now the problem with local register allocation is that it doesn't allow you to assign a virtual register to a physical register and keep the value across basic blocks. So if you have something like this, define R1, use R1, and you have in another basic block you have use R1. In local register allocation, there is no way you can assign this R1 and this R1 to the same physical register. Why? Because you are allocating each block separately. So you are invoking that local register allocation algorithm. You are invoking it on this basic block, and when it's working on this basic block, it doesn't know anything about this basic block or this basic block. And when it's working on this basic block, it doesn't know anything about what's in this basic block. So this means that when you do local register allocation, you cannot keep a value in a register and you keep it live across basic blocks. What you'll have to do in this case is, okay, you can probably allocate R1 to one physical register, like P1, for example. But here in this basic block, you don't know about this basic block. So anything that is used in this basic block will have to get loaded before it's used. So you have to load R1 here. The only way you can do it with local register allocation is to load R1 from memory. You have to load it from memory and then use it. This means that with local register allocation, you will have lots of loads at basic block boundaries. And in fact, you will have loads and you will have stores. You will need stores because in order for this to work correctly, we have to what? Where do we have to insert a store? Well, at the end of this basic block or after the last definition in this basic block. So in this basic block, this happened to be the last definition, right? So if this is the last definition, we should insert store R1. We can do it here. It doesn't make a difference in this case. So you can either put the stores at the very end of the basic block, or you can put them after the last definition of the basic block. So what does this mean? It means that when you do local register allocation, you will end up adding all of these loads and stores that will make sure that the values are stored in memory after a definition, and a value is loaded from memory before a use. Okay. Is the idea clear here? Why the difficulty of, or what's well, in fact, why local register allocation is not very efficient? Yeah. Okay. So in this case, when we have a register that is used in this basic block, but is defined in another basic block, we say that this register belongs to the live in set. So for each basic block, there is a live in set, a set of registers that are live at this point. So they're defined in other basic blocks but are used in this basic block. And the live in set here will have R1 in it. So if we had, for example, define R1. So if we had a define R2 and define, it's getting messy. Okay. Define R2, define R3. And we have a use R3, and we have a use R2 here. So in this case, in the live in set for this basic block, we have R1 and what is live in? Live in is a register that is defined in another basic block that is a predecessor basic block in the control flow graph and is used in this basic block. So in this case, what is live here is R1 and R3. While the live in here for this basic block is R2. Now what's live out of this basic block? So what is live out? Well, in fact, all of them are live out because they are used late. So live out is going to have R1, R2, and R3. Okay. So if you had, for example, if we let's extend it. Let's extend this basic block. So if we had a define R4 and use R4, and R4 is not used in any basic block below this. So let's call it basic block 1, and this is basic block 2, and this is basic block 3. So R1, R2, R3 are live out because they are used later in successor basic blocks. While R4 here is not live out because it's defined here and it's used here, and it's not used below this basic block. Yes?
Live out for R1, 2, 3 only because they've been stored?
No, because they are used in successor basic blocks, because R1 is defined here and used here. Okay. R2 is defined here and used here, and R3 is defined here and used here. So you will have a, you'll have a live range. So R1, the define for R1, you have this define R1, and this is use of R1. So this is a whole live range. And for R2, you have this live range. And for R3, it's defined here and it's used here. So you'll have this live range. OK? So live means live at this point. It means it has been defined above this point, but it will be used below this point. So this applies to R1, R2, R3, but it does not apply to R4. R4 has been defined above this point, but there is no use of R4 below this point. So live out means it will be used below this point, it will be used later, it will be used in a successor basic block in the control flow graph. While live in here, live in means that there is a register that is used in this basic block but was defined in a previous basic block or in a predecessor basic block. A basic block that is above this basic block in the control flow graph. Although the meaning of above and below may not make sense when we have cycles in the graph, right? Because if the graph has cycles, then you can no longer talk about above and below, right? So if you have something like this, then you can no longer say that this is above or below this. It's a cycle. Okay, but we are, at least, without the cycle, we can, above and below makes sense. It makes sense to say above and below. Okay, so any questions on the concept of liveness? Okay, so when we have live in and live out, registers, if we are doing local register allocation, we will need to store all live out registers. So store live out. So in this case, you need to store the live outs, and you need to load the live ins. So you store these. Why? Because in subsequent basic, this is when you are doing local register allocation. When we do local register allocation, we must store all live out regs at the end of the block and load all live in registers at the start of each block. At the end of each block. So for each block, we will find the live in and live out. How do we find the live in and the live out? There is an analysis for finding live in and live out. We will not, it's not in today's lecture covering how we can compute the live in and live out, but it's something that we will be covering in a future lecture. Okay, so this is what we need to do with local register allocation, which means that we will have lots of loads and stores that may be avoided. If you can do global register allocation, look at all basic blocks at once, you may be able to avoid all of these stores for the live out and these loads for the live ins. Okay. So let's look at an example. So these are virtual registers. A, B, C, D, and E are virtual registers. Okay. Now let's look at the live in and live out sets. Okay. So for this basic block, live in, there is nothing live in. So live in, so we are assuming that this is the entry basic block. So live in here is going to be the empty set. Okay. Now, what's live out? Live out means something defined here and used later. So, yeah, just A. Why? Because E is not used in any of the subsequent blocks. So live out is going to be A. Now, what's live in here? What's live in?
Nothing.
No, it would be A.
It could be.
Yeah, well, still be A. Still A will be live because even though A is not used in this basic block, it is still used below this basic block. So there is a live range, like, try to imagine the live range. So there is a live range that is going this way. Okay, so this live range, this is a possible path in the code. So if this path in the code is taken, A will still be live here because it's used here. It's not used in this basic block, but it's used in a successor block. So A will still be live in this case. Okay, so live in is going to be A. Live in here will have A. Now, what's live out for this?
A and D.
Yeah, so live out, A is live because it's at this point it's live, it's defined here. So A is used below this point and D is used below this point. So A and D both are live out, and same applies to this. live out equals A and D. Okay, and these, in fact, in general, the live in for this will be in general. What will be the relation between live in for a node, for a basic block like this, and the live outs of its predecessor basic blocks?
It's equal.
It's the union of all.
Well, the union, exactly. Generally speaking, it's going to be the union. So in this example, they happen to be the same. So the union is going to give the same set. But generally speaking, what is live out, what is live in here, is the union of these live outs. So if we had a C here, or an F, or a G, would have added it to the live out of this. So live in, sorry. Live in here equals A and D. Okay? So now we know the live in and live out. Now remember, now we are trying to do global register allocation. So we are trying to avoid spilling the live outs and loading the live ins. So when you do local, you spill or you store the live outs and you load the live ins. Now with global register allocation, we're trying to avoid this. And we're trying to keep these virtual registers in the same physical register across basic blocks. So we would like to keep A in a register, and we would like to keep it in a register until it's used here. Okay, so throughout this entire live range of A, this is the definition and this is the use, we would like to keep it in a register. So before we look at the live ranges here for the global, let's look at live ranges in the local sense, just because it's easier. Before we look at global live ranges, let's make sure that we understand local live ranges. So if we have things like, in the same basic block, define define A, use A, define B, use A, use B, define C, use A, use C. If we have a sequence of defines and uses like this, the live range is going to be start at the definition and it will end at the last use. So the live range for A is going to be this. This is live range for A. The live range for B is going to be, this is define B, this is use B. There's only one use of B. So this is live range of B. And what about C? C is defined here and is used here. So this is the live range of C. So within a basic block or in straight line code, live ranges are actually live intervals. So in straight line code, or within a basic block, live ranges are live intervals, which means that they are linear. Everything is linear. Now why are live ranges interested for register allocation? Why do you think when we do register allocation we care about live ranges?
So you don't, because if you're going to use a value later on in that block, you need to have it in the register so it can be used.
Okay.
But if a value is no longer needed, it can be dumped for a different value to be used for something else.
Okay. But how does the notion of live range help us with this? So we're trying to map virtual registers to physical registers. And we have these live ranges. So if we have two live ranges that overlap, then what does this tell us about the allocation to physical registers? So in this case, for example, the live ranges of A and B overlap. So there is an overlap between the two live ranges. This means that you
need at least two physical registers.
Yeah, two physical registers. They cannot be placed in the same physical registers. So the key idea is, if two live ranges overlap, if the live ranges of two virtual registers overlap, you cannot put them in the same physical register. Okay? If the live ranges of two virtual registers overlap, you can't put them in the same physical register. So in fact, this is often, compilers often represent this by a conflict graph or an interference graph. So in this case, A conflicts with B overlaps with B, but does A overlap with C?
No.
Yes, A overlaps with C, but do C and B overlap? No. So B and C do not overlap. So if we draw a conflict graph like this, conflict graph, sometimes it's called conflict graph, sometimes they call it interference graph. Okay, just another name. So because it shows conflicts or interferences, so here A and B conflict. So there is an edge that indicates that A and B conflict with each other, and A and C conflict with each other, but B and C do not conflict with each other. Now, in order to allocate physical registers for these virtual registers, we can think of this problem as a graph coloring problem. So how many people are familiar with graph coloring? Okay, so what does it mean? Yeah.
The graph coloring problem is like you have like a map and you don't want two colors to touch each other.
Okay. So here we don't have a map, we have a graph. So in the context of a graph, what does it mean to color it? So we don't, yeah, it's the same idea. The same idea. Where in the map you don't want, two countries that are next to each other, adjacent. You don't want them to have the same color. You want different colors. So adjacency in the context of a graph is represented by edges. So A and B are adjacent. So we don't want them to have the same color. So we can say, okay, this is red, and this has to be a different color. This is blue. Now C is adjacent to A, right? But it's not adjacent to B. So adjacency in the context of graph, it means there is an edge between them. X and Y are adjacent if there is an edge between them. So now C can be colored blue, but you cannot color it red, right? So this is the graph coloring problem. So now in this case, these colors will correspond to what in the context of register allocation?
They would correspond to physical registers.
Physical registers, yeah, exactly. So now colors correspond to physical registers, and these nodes are virtual registers. And we would like to do this coloring using the minimum number of colors or minimum number of physical registers. Now, in general, for a general graph, the graph coloring problem is NP complete. So graph coloring is NP complete.
Oh boy, that's
Okay. So which means that there is no polynomial time algorithm, there is no known polynomial time algorithm that will take an arbitrary graph and color it optimally using the minimum number of colors all the time. So it's, you may find an algorithm that will give you the minimum number of colors for, say, 99% of the instances, if it's a good algorithm. So it will give you the minimum number of colors for 99% of the instances, but not for 100%. So there is no algorithm that is guaranteed to give you the minimum number of colors for every single instance that you can input to that algorithm. Okay, so, well, but there are heuristics. There are heuristics for doing graph coloring. So there are reasonable heuristics for doing graph coloring. Now let's switch to the global problem. So far we have been talking about this local problem. We understand what a live range means. We understand why we are interested in the conflict between live ranges, or the overlapping or interference between live ranges, and the relation between register allocation and graph coloring. How you can think of the register allocation problem as a graph coloring problem. You want to color this graph using the minimum number of colors. Now, what applies to local register allocation applies to global register allocation, but here the notion of a live range is more complex because it's no longer linear. Our live ranges here are no longer linear. For example, the live range for A is going to split here. Right? A is defined here, and it's live here and live here, and then so it's going to split, then it's going to merge. So a live range in the global context, in the context of a control flow graph with multiple basic blocks, it is not going to be linear. But still, we can talk about live ranges, even in the context of global. So now, for example, the live range of A is going to be like this. So A is defined here, and this is the last use of A. So A, you can think of the live range of A as it starts here, and then it goes through all of this basic block, and it ends here. But this is not the only path.
Yeah, it's actually used in that other mid-range block too, A.
Yeah, and it goes here, and it goes through this, but it keeps going because it's used here. So this is what the live range of A looks like. It's not a line. It's not an interval. It's not linear. It looks more like a web. Sometimes they call the live ranges in the global context webs because you'll have lines all over and they split and then merge, and so they don't look like lines. So this is for A. Now the live range of E, because E is not used in any other basic blocks, so E is basically defined and used locally, right? So its live range is going to be an interval like this. This is the live range for E. The live range for B, so B is defined here and is used here. So B is another local live range, which is an interval. For C, another local one. But for D, so D is defined here, so its live range is going to be this, but there is another live range, another line, which is this. Okay? So what does this mean? It means that when we look for the conflicts or the overlaps between live ranges in the global context, we have to be more careful. So let's see if we can determine now which live ranges interfere and which don't. Because if we can draw that interference graph, then we can think of the problem as a graph coloring problem. So let's construct the interference graph. Let's start with A. So with which live ranges does A conflict? So okay, A and B. Does it conflict with B? Yeah. So A goes this way. So in fact it's conflicting with everyone. So it's conflicting with B. It's conflicting with C. It's conflicting with E. It's conflicting with even with D. So if you look at the live range for A, it overlaps with all other live ranges because it's very long, and and this is the last use of A. So A is gonna conflict with all. It's gonna conflict with B. It's gonna conflict with C, D, and E. It conflicts with all of them. Okay, so this is a this part of constructing the conflict graph is something that has to be done carefully because it's kind of tricky. Okay, so we know the interferences of A. Now, what about B? So maybe we should ask the question: with which other live ranges does B conflict?
D.
It conflicts with D. Does it conflict with A? Yes, it already conflicts with. So B conflicts with D. Okay. So if we look at C, so here's the live range for C, with which
Just A.
yeah, it only conflicts with A. So we already have an edge from C to A. Now, what about D?
Just A.
Well, it conflicts with A and it conflicts with B, but both of these conflicts have already been captured in the graph. Now, what about E?
Just A.
It only conflicts with A. So this is going to be our conflict graph. Now, looking at this conflict graph, of course, with simple instances like this, we can easily figure out the optimal solution, right? So we only have 5 nodes. So by inspection, we can figure out the optimal solution here, the minimum number of colors. What's the minimum number of colors that we need here?
3.
Yeah. Why is it 3?
There's 3 connected nodes.
Yeah, exactly. Because A, B, and D, so these are connected. So these are all not only connected, but each one of them is connected to the 2 others. So this subgraph in red, what do we call this?
That's a cycle.
A loop.
When a number of nodes are all connected to each other,
A complete graph.
well, it's a complete subgraph. So what do we call it? What's the name for a complete subgraph? So have you heard of clique? It's a clique. So this is a clique of size 3. So clique, it's a subset of the nodes that are all connected together. They form a subgraph, a complete subgraph. So this is clique. So if we have a clique of size 3, a clique that includes 3 nodes, this means that you cannot do it with less than 3 colors. So at best, you will need 3 colors. So if in this case, if the target machine has 3 physical registers or more, we don't have a problem. We can color this, assuming that the graph coloring algorithm is going to discover the best coloring. And there are good heuristics for doing graph coloring. They are not perfect because it's NP-complete. The problem is NP-complete. But there are good heuristics that will discover the optimal solution most of the time, for most instances. So assuming that we have a good heuristic and we have 3 physical registers, we have no problem. We can color them. So we can say, for example, that this is blue and this is red. and this is maybe green. Okay, and C, you can give it any color but blue, so you can color it red. And E, you can color it any color but blue, so you can color it red. So this is if you have 3 physical registers. What if you have 2 now? What if you have 2 physical registers? So what will make sense to do if we have 2 physical registers? Well, in this case, having 2 physical registers means that you cannot, there is no way you can allocate a physical register for every live range. So you have so many conflicts that you cannot keep each live range in a physical register. Now, before we move to this, remember that if we have 3 physical registers here and we manage to to map each one to a physical register, now we have this you will put it in one physical register and it can keep it through all basic blocks. So unlike local register allocation, you will no longer need to do stores here and loads here. Okay, so if you have 3 physical registers, you can keep A in a physical register, and you don't need to store A here and load it here and here. Okay. Now if we have 2, we have to victimize one live range. Right. And the live range that we will victimize is going to be one of 3 live ranges, right? The ones that have this big conflict. So these 3 cannot be kept in the same register at the same time. So we need to victimize one of them. Now, what will make sense to consider when selecting a live range to victimize or to spill, to make a spilling decision? Well, compilers will look at how, the cost of this spill. So how much they will estimate the spill cost. What's the spill cost? The spill cost is how much it will cost me to spill this live range. And spilling a live range means you insert a store after every definition and you insert a load before every use. So spilling a live range means inserting a store after every definition, spilling a live range of X, spilling the live range of X means inserting a store after every definition of X and a load before every use of X. So in this case, for example, if we choose to spill A, spilling A, we haven't decided to spill A yet, but just assuming that A will be the register that will end up getting spilled, we will put a store here, store A, after the definition. And this is a use of, no, there is no A here. There is a use of A here, so what do we insert here? Load. Load A. And what else?
There's one more use.
Yeah, there is a use, so what do we insert?
Load.
Load. Load A. So what spilling means is that we haven't decided this for A yet, but if we end up spilling A, we will put a store after A, after every definition, so that we store it in memory, and we put a load before every use. What does it mean? It means that we spilled it to memory. It's no longer in a register. And A is no longer in a register. And it means that after we are done with it, we just put it in memory. And whenever we need it, we have to load it or fetch it from memory. Okay, so this is what spilling means. Now, given this definition of spilling, or how spilling is implemented, will it make sense to spill the register that has lots of definitions and uses, or the register that has fewer?
Fewer.
Yeah, the one that has fewer. Because the one that has fewer definitions and uses will require fewer loads and stores. Our objective is to minimize the number of loads and stores that we will be inserting into the code. So we prefer to spill the register that has fewer defs and uses, but the number of defs and uses is not the only consideration. We also have to take into account what? Well, not all basic blocks are going to get executed the same number of times, because some basic blocks may be inside loops, some basic blocks may be outside loops. So if a register is used only once in a basic block that is inside a deeply nested loop, then that load that we will be inserting, that load will get executed a large number of times. So if there is a block and this block is inside of a loop, and we just put one load here, and this loop gets executed 1,000,000 times, then this load will get executed 1,000,000 times. So we'll have to take into account the frequency of execution of the loops, if we know that. Of course, at compile time, remember that all of this is done at compile time. So the compiler doesn't know precisely how many times each basic block will get executed, because not all basic blocks, not all loop trip counts or loop, the number of iterations of the loops, not all of them are known at compile time, right? So you can have something like this: for I equals 0, I less than x, I plus plus, and we have a loop, and then read x. So x is read from the input or from a file. So if x is read from the screen or from a file or whatever, at compile time, when the compiler is looking at this, it doesn't know how many times this loop will get executed, right? Yeah. So in general, the compiler doesn't know at compile time how many times a loop gets executed. It doesn't know how many times a basic block will get executed, but usually it comes up with some estimates. And it can distinguish between basic blocks that are inside loops and basic blocks that are outside loops. So if there is if there is code in here, a basic block here, then we know that it's inside the loop, and most likely it will get executed more frequently than other basic blocks.
So it gets a higher priority for register allocation.
Yeah, exactly. So we try not to spill. We try not to spill inside loops. We try to spill outside loops. And again, spilling, adding these loads and stores. We try to do it outside loops, not inside loops. But the point that I'm trying to make here is that at compile time, the compiler doesn't have precise information. It may come up with some estimates. So in fact, register allocation will be based on these estimates. So if the compiler comes up with, for example, this basic block will get executed once, and then it will split. So this is going to be half, will have a weight of a half, and this will have a weight of a half. But this is inside of a loop, so this is going to get executed 10 times, for example. So the register allocator is going to do the analysis based on the execution frequency with these estimates that are, like I said, usually are not accurate. Now, given these estimates, which register do you think it will be spilling?
D.
Yeah. Well, no, D is here. So D is here. So A and D are here.
B.
Yeah. So B, because B is the one that is outside the loop. So if it spills B, B is only in this loop, and it will insert, a store here. Store B, and here it will insert what?
Load.
Load B.
Oh, okay. I see.
Okay. So in this case, it's going to split this live range. Now, the live range of B is this and this.
Oh.
So now, if it does this, B will no longer conflict with. Will it still conflict with D?
On D.
It will still conflict with D and A. So in fact, what this means is that the with this algorithm, we will identify the live range that is least expensive to spill, which is in this case B. We spill it, and then we try again. We construct the conflict graph again, and we try to color again. This may or may not help. So the spilling may or may not help, may or may not make things easier. Things may continue to be hard. And in this case, it didn't help. So if it doesn't help, it will make another decision. Okay? It will try now to spill the next cheapest live range to spill. And now it's not obvious, so we'll have to do some calculations. In fact, in general, it's one way of calculating this is to count the number of loads and the number of stores, and to multiply each load or store with the execution frequency of that basic block, and that will give you an accurate estimate of the spill cost. And since we are running out of time, we will not get the chance to do this in detail. But if you do this, if you count how many stores and loads you will need, and then you multiply each one by the execution frequency, you will get a higher cost for A, because A has more definitions and uses than D.